In the first lecture, we guessed, in some sense, the form of the Schrödinger equation, relying on a few very basic experimental facts, such as wave-particle duality and the dispersion relation of a free electron. But we didn't talk too much about the meaning of the main object that appears in this equation, the wave function, which was introduced in an ad hoc fashion. So today I'm going to talk about the actual physical interpretation of quantum theory formulated this way. And we're also going to introduce a few very important standard notations and conventions that are going to be used throughout the course, and also that are routinely used in the standard literature on the subject. So here is the Schrödinger equation. Once again, we're going to see it very often in this course. And I'm also showing here a part of the first page of the original paper by Schrödinger, published in December of 1926. And it's actually very interesting how Schrödinger came up with this work and this equation. So apparently the story started back in 1925 or so, when he was working under Debye. And Debye had just read a paper by de Broglie, where de Broglie was introducing his wave-particle duality ideas. So he got interested in these ideas and suggested Schrödinger to give a seminar on de Broglie's work. So apparently Schrödinger actually dismissed this at first, saying that he didn't even want to think about such a silly theory. But he had to give in because, well, Debye was effectively his supervisor. And so he was looking into de Broglie's work, trying to present it in a more mathematically sophisticated form. And in doing so, he came up with the Schrödinger equation, essentially, as we now know it, and which brought him the worldwide recognition and Nobel Prize in Physics in 1933. So another important thing that Schrödinger did was that he used his equation to solve a very important problem of a charged particle in a Coulomb potential, which essentially describes a quantum hydrogen atom. And he found the energy level structure, which was consistent with the Bohr's atom. And so actually Charles Clark is going to talk about this solution later in the course. But I'm going to just mention here that this was indeed very important, and it was a clear smoking gun that Schrödinger was on the right track. But according to Debye, at least, quite interestingly, Schrödinger didn't really understand the true meaning of his own work. He actually dismissed even the importance of it at first. So I don't know if it was just Debye being jealous or it was true, but certainly if you actually read the original paper by Schrödinger, you don't see too much insight into the true physical interpretation of his own equation. The correct interpretation of Schrödinger equation was developed very shortly after Schrödinger's work by Max Born. Perhaps actually I should say not the correct interpretation, but the commonly accepted interpretation, because scientists actually have been arguing about the interpretation up to these days, and some are still not convinced that the Born interpretation and the Born rule that I'm going to present is the only correct view of quantum physics. But certainly this Born rule is the cornerstone of standard quantum theory, and it is indeed consistent with all experimental data as we know it at this stage. Now, before formulating this rule, I would like to make a few general comments about quantum physics and make them in contrast to classical physics. So in classical physics, if we have a classical system, let's say this is a closed classical system with some classical particles moving around, and if we know everything about this system, let's say we know all the coordinates of all the particles at a certain moment of time and all the velocities at a certain moment of time, then classical theory predicts with absolute certainty the result of any conceivable experiment that is going to happen in the future, which is determined by, let's say, trajectories of particles at any subsequent moment of time. And they in turn determine all possible outcomes of all possible experiments. Now, this is the classical system. So the truth about the quantum system, so if you look at the actual situation with quantum systems, so if you have a quantum system like that, so with some wave function psi. So even if we know everything possible about this quantum system, that is, if we know psi, and if we know all the forces, everything about the system, we still cannot possibly predict with certainty the outcomes of well-posed experiments. Let's say if we have some detectors here and they measure, let's say detect electrons or some other particles. So even if we know everything about the quantum electrons, we still cannot predict for sure which detector is going to pick up electron at a certain moment of time. And so this uncertainty is intrinsic to quantum physics, and there is no way around it. And so Born realized it, and he also found a way to quantify this uncertainty using the wave function. And his, what we know now as the Born rule is written here. So basically he proposed, and afterwards it was confirmed, again by comparing with experimental data, that the absolute value of the wave function evaluated at a certain position in space and at a certain moment of time gives the probability density of finding a quantum particle described by this wave function in at this position and at this moment of time t. Well, the probability itself is going to be psi, absolute value of psi squared times the volume, the elementary volume in the vicinity of a certain point. This work of Max Born turned out to be extremely influential and groundbreaking, and he eventually received a Nobel Prize for these ideas, in part, in 1954. As a matter of fact, he should have received this award much earlier. He was nominated by Albert Einstein, actually, back in the 30s, but he didn't get it due to some political reasons. But in any case, this probabilistic interpretation was and actually remains a very remarkable feature of quantum physics, which also is a source of confusion oftentimes. And I'm actually supposed to tell you now about this probabilistic property being a mystery of quantum physics, and something which we will never be able to understand. But I would actually argue otherwise, that there is in fact nothing mysterious about it. If by mysterious we mean something that is not consistent with our everyday intuition and everyday experience, so actually uncertainty is a part of our everyday life. Whether we are dealing with a sporting event or any other event in our life, we can predict with certainty, even if we know everything, how it's going to turn out. And so I don't see a reason to demand from science deterministic answers. And nature just doesn't work this way, and so we should just accept this fact and get used to it.